Hello, everyone, and welcome to this Cassandra community webinar from MongoDB to Cassandra Architectural Lessons. Before we get started, I wanted to draw your attention to a new free online resource that we have. If you are new to Cassandra or want to learn more about it, we have free online training. I will show this link at the end of the webinar as well. The first course is Java Development with Apache Cassandra, and we are releasing new modules every single week. So now I'd like to introduce Blake Eggleston and John Haddad, great friends of the Cassandra community. This is actually the second webinar that Blake and John have done about their migration from MongoDB to Cassandra. As always, we will leave questions for the end of the webinar, so if you have a question for John and Blake, please use the Q&A tab inside of WebEx, post your question there, and we will reserve time at the end to get through as many of them as we can. So John and Blake, welcome, and you have the ball. Take it away.
All right. Hey, guys. I'm Blake Eggleston. This is John Haddad, and we're going to be talking about some architectural lessons from MongoDB to Cassandra. Today we're going to be covering initially some differences in the architectures between the two databases, and then we're going to go into a look at some of the internals of our applications and discuss some of the more interesting ways that we are using Cassandra to solve some problems we have. And finally, we're going to talk about cqlengine, our Python object row mapper that we've developed in-house and that we use in all of our applications to talk to Cassandra.
Which is open source as well.
Yes.
Okay. So starting out on the MongoDB architecture side of things, there's a couple important concepts that we should really go over. So at the smallest unit, you've got a single Mongo server, which I think everybody's aware of. You can build a Mongo server. You put a bunch of them together. You can create a replica set, which is just a master-slave configuration. So once you take those replicas, if you take a bunch of replica sets together, and then you can put them together to form a cluster. So the individual replica sets are considered shards, and they basically just hold. Each shard holds a portion of your data. To manage the cluster, you have these config servers, which handle the network topology, basically it determines which keys go onto which shard. To connect to the cluster, you have to use this Mongo's process, which generally lives on your app server, which is basically like a router or proxy that talks to the config servers to determine which shard you need to talk to perform a query. Then you have a shard key. So on any document, or on every document, you have an indexed field, and that index field is going to determine which shard a particular document belongs to. In most cases, it's going to be the ID of the document, but you can use other index fields, and there's advantages and disadvantages to changing them.
All right. Cool. So in contrast, with Cassandra, there is only one type of server, which is just the Cassandra server. There is no master or slave. And Cassandra sets itself up as a token ring where each node is responsible for a certain range of tokens in the in the hash ring, basically. So each node is responsible for a certain range, and then it replicates its data forward on the ring to the next 2 or 3 nodes, depending on what your replication factor is. We use 3 here, so that's what we use for all of our examples. So the advantages of this is you have no single point of failure. If a node just disappears, goes down, it's not a big deal because the data has been replicated. Cassandra will automatically start routing queries to different nodes, and everything's okay. So when you're doing reads and writes, these keys cached to a particular location on the ring, and this will limit the query flexibility a little bit because you always have to query by the row key so that it knows where on the ring to route the query to. Finally, each query has a consistency level, so if you want to be kind of wild and just fast and loose your data, you can do that, and it'll only wait for a reply from a single node, or typically you'll want to use something like quorum, where it waits for one more than half of the replicas to respond to either a read or a write, so you know that your data is has been persisted to at least half of your replicas.
Yep. So at the heart of each Cassandra server, you have your storage model, which is important to get into and understand, and you have to know this in order to build your tables efficiently. So one thing that's very important to keep in mind is that SS tables, which are the file level storage for Cassandra, they're immutable. So once they're written, they're never changed. There's some really, really cool advantages to this, one of which being it's harder to get corrupted. Another one is it makes backups super, super easy. Because once an SS table is written, all you have to do is copy that table somewhere, and you're good to go. With each piece of data that's written, you have a key, and you have a column, and then you have a value. Now, you also get for free a timestamp of when it's written. So because you can't edit an SS table in place, what you do is you actually end up writing the same data, you end up writing the same key and column combination to multiple SS tables. And that's actually not that big of a problem. So basically what happens is when a read happens, you end up reading in several SS tables, and the column with the newest timestamp wins. So you're probably wondering, what does that mean? Is that efficient? What happens with multiple copies of the same column? Well, there's something called compaction. And what compaction does is it takes multiple SS tables and it will merge them into a single one. And this just basically gets rid of the duplicate column values and just takes the newest one. So the other thing to keep in mind is with a distributed system like this, there's a concept called a tombstone. So a tombstone is basically like a null value. It basically says this data has been deleted. Essentially what this does is it allows you to not have to worry about what happens if one of my servers doesn't get the delete. Your ghost data won't come back like a zombie, which is not cool in real life or in databases.
Okay, so now we're going to talk a bit about what happens when you execute a write against your Cassandra cluster. When you execute a write, you can execute against any node in the cluster, and that node then becomes the coordinator, and it will figure out, based on the key, which node this write should go to. When you perform a write, the write is saved into a mem table, which is basically a portion of Cassandra's database that lives in memory. And then it's also written to a commit log. And then mem tables are periodically flushed to SS tables. One thing to note about the commit log is that it basically maintains a running record of every mutation you make to your data set. So you don't have to write an SS table every time there's a write. You have a set of SS tables and you have a commit log. If your node turns off, when it turns back on, it will basically replay the commit log to bring its understanding of your data set to where it was when your node turned off. So here are Cassandra Reads. As far as the way the cluster behaves, on a network level, it's pretty much the same as writes. You can read from any node, and then that node will go out and talk to the nodes that actually own the data. When you do a read, data is pulled up from multiple SS tables, and then Cassandra will then reconcile the timestamps of columns against the different SS tables, and also its in-memory mem tables to form a up-to-date picture of your data, which it then returns to you as the answer to your query. It may also perform a read repair if there are inconsistencies in the data it gets back. And so one thing to also point out is that reads are more time-consuming than writes because it's not just going out and appending to a commit log. It's actually going, doing disk seeks, pulling data in, looking at it, and then sending it back over the wire to be reconciled on the coordinator.
Okay. So for those of you familiar with MongoDB, you probably know a lot of these advantages. There are, I think one of the things that's touted for Mongo as its big advantage is it has super flexible documents. So I think a lot of people, when they're talking about data modeling with Mongo, they don't really need to take into consideration how your data is stored. So because you can query it so flexibly, you've got a lot of flexibility with your indexes, and as a result, your queries, you can do a lot of really crazy stuff. You can search on embedded fields. You can do full text search, geospatial queries, and there's an aggregation framework as well as their built-in MapReduce. So at the surface, there's a ton of flexibility that you have available to you. And they've been around for a while, and they've done a really good job with their documentation. So they make it pretty easy to get started, and they make it really easy to learn how to use the tool. So they definitely have that going for them. But on the flip side, you end up having some of this flexibility, I feel, sometimes introduces certain problems. And one of them is because you have such wild query flexibility, you don't realize that in a clustered environment, a lot of the queries that you're going to do that are so flexible will actually end up routing to the entire cluster. So every shard will actually have to execute a portion of the query, and the results will come back to the Mongo's process. Now, the downside here is that it's harder to scale linearly when every shard is being contacted to answer a query. So really what ends up happening is this whole flexible data model ends up becoming a lot more simplified. So all those features that they tout as being really cool and useful, you end up not using them because once your data hits a certain size, it's just impractical. When you write documents, if you're doing updates and your document size is constantly growing, you'll actually end up allocating more and more memory, which will be a problem. You need to do the DB repair in order to fix this or restart your server. Basically, you can end up with a lot of really crazy problems. I feel that the query language is also extremely complex and hard to write by hand. So coming from a SQL background, initially, like I got used to being able to type my queries at the command line. And with a database like Mongo, it's practically impossible. Writing a very like bizarre JSON document style query is kind of a nightmare. And the other thing that I think is important to keep in mind is that because you don't have as much control over how your data is actually stored on disk, you can end up doing a lot of seeks. So with Cassandra, you have a ton of control over your data and a ton of control over your disk. And when you do a query with Mongo, you don't know if you're going to get your best case scenario, which is all your data is in memory and it comes back really fast, or you're going to get your worst case scenario, which is we have to do a ton of seeks, pull your data out, and it's just super slow in those cases, and just ends up dragging everything else down. The advice of Mongo is to not go over 256 gigs per collection, which is honestly not that big if you've got a serious business and you're really like working with a lot of data. So you end up having to do a lot of manual sharding of your data, and you still have to take into account your data model, and it doesn't, like I said before, it does not give you the total flexibility that they really emphasize that it does. You have to use a very small subset of their features.
Okay, so with Cassandra, some of the advantages is that first it's multi-data center aware, and it's had that for quite some time, so it's pretty reliable. As we saw with the cluster architecture overview, there are many fewer moving parts. There's one type of server you have to worry about. You also don't have to worry about any sort of locking at the database or table level. And because of the way that it stores data on disk, time series data or any data that needs to be sorted is super, super, super fast. Also, because of the way that the coordinator node talks to different nodes when it's looking for a key, you can scale pretty much linearly as you add servers to your cluster. And it also has compaction options for your SS tables that are optimized for either your traditional spinning disks or for SSDs. And like I mentioned, you have a ton of control over how your data is actually stored on disk. So some disadvantages is that the secondary indexes have some hidden costs, and you really need to understand what they're doing and what your queries are going to look like before you decide to use them. Individual reads are not as fast as other databases because of all the reconciliation that it has to do. But again, when you're talking about data that's sorted on disk, it's much faster. The JVM can be a little tricky to work with. It's fine to start up a cluster and get it working, but once you start getting into performance tuning and stuff, there's a lot of understanding about the JVM that you need to have to do that effectively. Also, and this is kind of a disadvantage, kind of not, but the laying out your tables and data modeling requires a bit more planning. You kind of need to know up front what kind of queries you're going to be doing before you start laying out your tables. And this makes ad hoc queries a little trickier, especially stuff with lots of permutations or parameters. A lot of times you'll need to make a table for each query that you do. But we internally complement Cassandra with Elasticsearch, which for these wild queries is really, really good. And then I know that Solar is also an option there as well, and that comes with DataStax Enterprise as well.
So we're going to cut now into a couple real-world examples, how we use Cassandra here and why it's a better tool for us than Mongo or alternative databases for that matter. So the first thing that we're going to look at is our Media Manager tool, which is for social analytics. So Media Manager is an ad buying tool that we have and management tool for Facebook and Twitter. We sync 2 billion ad stats a month, which we perform constant roll-ups on. So as soon as we get our data back from Facebook, we roll it up at several levels. And we're actually syncing each ad that we've published on Facebook or we know about, we're syncing all of its data back roughly every 5 to 10 minutes. So it's updated with Facebook every 15, and we catch it almost immediately, and we're totally up to date. All this is happening on a 10-node cluster, and we're running in Amazon the high I/O instances. So we are taking advantage of SSDs now. The highest our cluster is in right now, we had 150,000 queries per second executing against the cluster, and it performed admirably. So we're really, really happy with that. And right now, we've got 150 gigs of data, but that's growing right now at a rate of 10% per week. So it took us a little while to get that ramped up, but now we're expecting to have several terabytes of data sometime next year. So we're pretty excited about that. And we've done some testing with adding more nodes than this, and everything has performed really, really well.
Right. So I think we're actually closer to 200 gigabytes as of last night. So, okay. So with this ad set collection, we need to be able to do aggregation. The ads are kind of stored in this hierarchical structure in Media Manager where you belong to a team. The team has folders. The folder contains campaigns, and the campaigns contain ads. Now, the ad stats are collected at an ad level. And as soon as an ad stat comes in, all of those parent containers basically need to have their their stats updated as well. So if we get an ad, we want to make sure that the team's stats that contain that ad are updated immediately. Now, clearly going and doing some sort of, iterating over every folder, campaign, and ad is just totally impractical, and it's just not going to work. So we've come up with this this method for doing the rollups, where we have a set of tables that contain all of the ads and stats for a single campaign and date. And so when we collect a stat for an ad, we go in and we update the stats for this ad, okay? And then since this is all a single physical row on disk, we read out that entire row with one disk seek and do an aggregation on it, and then write that aggregation write those aggregated values into a similar table that has a folder and date, and then the campaign stat. And then we do that again and roll that back up into the team. So by structuring our data this way and our queries, we are able to, every time we get an ad, really quickly roll up the campaign into the folder, into the team, with something like probably 5 to 6 reads and writes.
Okay. So for us, Cassandra is definitely the best choice to store all this data. Effectively, our entire database is in our working set because we access it literally every 15 minutes. Every single piece of data is touched constantly, and we can't have the worst case scenario of when our data is not stored in memory, hitting tons of different locations on disk, incurring the penalty of multiple seeks. With the solid-state drives, it's not as much of an issue, but still streaming data from a single point in disk is going to be much faster than doing a bunch of random I/O lookups. So one thing that made it impractical to use Mongo is that the data that we store is inconsistently sized and constantly changing. So the heuristics that Mongo uses in order to allocate memory for documents is not very helpful for us because the document sizes, because the rows actually change unpredictably. So if we were to use Mongo and we were to try and stuff everything in one document, we would be allocating many, many instances of memory, and we would have a lot of memory leaks. At least that was a problem when we were doing this before. So basically what we end up with is unpredictable query behavior and lots of memory fragmentation. Okay, so now we're going to talk a bit about Shift. Shift is our other product, and it's essentially a real-time messaging platform, and it's built for marketers. And what it does is it allows people to communicate across organizations and departments in a single place or team. Additionally, there are a set of third-party applications that work on top of Shift and use it via its APIs. And these are also able to communicate with these teams, and then in the future they'll also be able to communicate with themselves. Okay, so the interesting component of Shift right now is our messaging platform. So a message, when it's sent to a team, is fanned out to everybody on that team. And a team may have hundreds of people on it. I mean, we've designed this thing to handle hundreds or thousands of people from a technical standpoint. As a result of this, each person has a perspectival view on the message. So there's a lot of metadata that surrounds the messages themselves, whether or not it's unread, what tags they have on that message, several other components. So we end up doing a lot of writes. And basically, we're doing this in a way similar to, think of it kind of like a Twitter stream. So when someone sends a message, when someone tweets something, it goes out and everybody that's a follower gets it. So the way that we've architected our message inbox is we're actually utilizing the time UUID column type that's available in Cassandra. So a time UUID uses the UUID1 algorithm, which includes an embedded timestamp within the UUID. And this is really useful because when you look at the way Cassandra can store data on disk, if you use the time UUID option, it will actually store your data ordered by the timestamp portion of that UUID, which makes it really, really, really convenient if you want to do any sort of time series data, or in our case, just this message stream. So you can see in our diagram right here, our messages are out of order. So it's not enough to give them, to push messages to each person. We actually have to keep track of the timestamp that each person has for that message, because it's actually possible to have a message bumped up for one person and not others. There can be side conversations. Due to the way that we utilize these time UUIDs, it's really, really, really easy and fast to do a query for the first N items in a user's inbox, because it's essentially taking the head of a list. Super fast, really awesome, and has been really, really great for us performance-wise. And then finally, the inbox is not the only view that we have. We actually store about a dozen different pre-allocated views of a message that we call tags. And these tags are mostly internal, but we use them to surface messages in different contexts. So if you're looking at a team, you see it one way. Unread messages, you see it a different way. So it's been really, really useful for us.
Okay, so now we're going to talk about cqlengine. cqlengine is our Python CQL3 object row mapper, basically a ORM for Cassandra. So it right now it supports Cassandra 1.2, and it basically builds queries for you. It builds CQL queries for you, and right now we support TTLs, per query consistency, blind table updates, batch queries, counters, and all the collections, maps, sets, and lists. In addition to that, it will also manage your schemas for you. It'll create tables that you define as classes in Python, and it will also update your schemas if you add columns to that class. Not automatically, of course. You have to tell it to, but it'll do it for you anyways. And you can also define compaction settings per table. And we just added a feature which allows for table polymorphism. What table polymorphism is it basically allows you to store multiple types of objects in a single table. So our big use case for this is we have we have an ad campaign, and then we have a bunch of ads in that campaign. Now, all those ads can be of different types. So, for instance, here we have page post ad, mobile ad, application ad. But we don't want to have to, store this in 3 different tables, and then, as a result, do 3 different reads every time we want to read the ads out of that table. So what the polymorphism does is it adds a column which indicates which type of row this is, and then as you query the table, cqlengine will instantiate those rows as the correct model when it comes out of the database.
All right, so coming up in cqlengine, we have a bunch of features planned. So right now, the system is only set up to work with a single Cassandra cluster, so we want to change that, make it so that if you've got 3, 4, 5 clusters, whatever you have, you can work with all of them. We want to get the native driver integrated. Right now, I believe it's in beta. When it's out, stable, everyone loves it. We'll definitely get it integrated in, and that's a really, really big deal for us. There's a ton of performance improvements that are going to come along with that, with prepared statements and just moving away from using the wrapper of thrift to execute CQL. It should be a ton faster. More configuration options at the table level. Like said, we support compaction options, which is really good because you can optimize for different disks. We want to take that even further. We're going to have key cache and row cache configuration. All the features available in Cassandra 2.0. They have their lightweight transactions through Paxos and conditional inserts. So we're pretty excited about that stuff. And we really want to start building a ecosystem for third-party plugins. So on the mailing list right now, there's talks of having a session, which is very similar to the way SQL Alchemy enables a session where you can have basically data all persisted at once, as well as an identity map, which basically lets you work seamlessly with cqlengine, and you end up getting back the same object, even if you query for it multiple times. So instead of going back to the database, this identity map will just give you the row that you asked for. And if you modify one, the other is changed as well, because they're just the same object. So that covers our cqlengine portion, and we thank you for listening. I think now would be now's our time to take some questions.
John and Blake, so much. Great presentation. So at this time, we would like to take questions, and we do have some already coming through. So guys, are you ready?
Yeah, definitely.
Okay. Jega asks, can you talk more about compaction? Why is it needed? How often? How does it impact performance during that time? Is the data consistent before compaction?
Sure. So compaction basically is a way of optimizing your reads. You end up paying there's a little bit of a penalty for I/O in a way. There are throttles to make sure that it doesn't impact performance. So if you have really, really fast disks, you can kick up the throttle, or you can disable it completely. It's very, very configurable. The two types of compaction are meant for different types of workloads. So if you have solid-state drives, you can end up using what's called leveled compaction, which will make sure that your data is stored in as few SS tables as possible for a given key. So it minimizes the amount of lookups you have to do. So it basically helps your reads be super fast. And again, the whole aspect of it is configurable. How many occur simultaneously, how fast it occurs. You normally don't have to worry about doing compaction because it will actually do it as part of the Cassandra process. So it will just run them for you. You don't generally need to run them. It is possible to start a major compaction, which will put all of your SS tables into a single large SS table, and this is if you're using size-tiered. And it will, everything will be super, super fast, but the downside of that is as you grow your data, it's less likely that one giant table will be compacted with any other tables, at least in size-tiered. So yeah, you basically don't have to worry about it too much as far as like a maintenance thing, but you do want to make sure you have it configured properly.
Okay, great. And this is one that I will answer. Will your slides be available afterwards? So I imagine you guys probably will make them available either on your blog and through SlideShare. But also, we are recording this session, and tomorrow on Planet Cassandra, we will post both the link to the video recording and also to the slides as well. Okay, so Stan is new to NoSQL databases. Welcome to the new world, Stan. Can you abstract SS tables using object relational mapping tools like Hibernate for Java or Entity Framework for .NET?
Not that I'm aware of.
So there are tools that you can use to read SS tables, but they're really not meant to be accessed directly. Like if you want, you could use the Java libraries directly, but it's really not meant to work that way. It's not like a CSV. You're meant to use the Cassandra process. So you would use, if you were using Java, you would use the native driver generally, and then from there, you would just use the results that you get back from the native driver. I'm not sure about the Java side of things, if there's something like Hibernate to take care of the ORM portion for you. Because we generally don't use a lot of Java, we're a Python shop.
Okay, great. Thank you. Randy is asking, missed the website location. So Planet Cassandra is the Cassandra community website. All general resources we make available there. So make sure that's planetcassandra.org. You can bookmark that page. All our past webinars are there as well. So John and Blake's first webinar around their migration can also be found there as well. Okay, so Tom is asking, how does your app access the query results from Cassandra, and what language is your app written in? He heard Python.
Yeah, our application is written in Python, and we use cqlengine to communicate with Cassandra. And under the covers, cqlengine uses the old cql thrift Python library. So that's how we do it.
By the way, have you guys looked at 2.0 yet, by any chance?
Feature-wise, yes. And unfortunately, we're waiting on the native driver to be integrated, the native driver to be released for us to put in cqlengine, and then we'll be moving forward.
It was a loaded question because I didn't want to ask something that you had no knowledge of, but Ajay is asking, will Cassandra support transactions in the near future? So I was wondering if you knew enough about lightweight transactions to be dangerous.
So not in the sense that a relational database would support them. They're considered lightweight transactions. Patrick McFadden actually did a much better job of explaining this than I could. I know that his video on this is available through Planet Cassandra's YouTube channel, and I assume on Planet Cassandra as well. He does a super amazing job at talking about the features of 2.0. So I would honestly just butcher it if I tried to explain it.
Steady on, he's not that good. Super amazing. Helen. And to everyone, by the way, that we touched on something there that's really important to understand in the NoSQL world is terminology can be very similar to the relational world, but the actual meaning is slightly different. So when you hear Cassandra supports transactions in 2.0, and Patrick does do a good job explaining these, it is not a one-to-one relationship with a relational database, meaning it's not exactly the same as a transaction in Oracle or SQL Server or MySQL. Gosh, lots coming through here. I don't know if you guys can talk about some of the customers who are on your Shift platform, but we have a question on that. Who's using Shift today?
I'm not sure if we can talk about that either. I can tell you that there are a lot of Fortune 20 companies that do purchase their Facebook ads through us. But yeah, I'm not sure if we can give out names with you. I'll probably just err on the side of caution and say I can't say anything.
But is that generally the target user? Very big enterprises that want to get sort of a holistic strategy going towards their social media marketing.
Yeah, I'd say so. I mean, the aims of the two applications are to make purchasing a lot of different Facebook ads a lot easier, and then obviously the aim of the Shift platform is to make communicating between multiple large organizations and departments happen as smoothly as possible.
Yeah, effectively, we're dealing with customers that may be buying tens of thousands of ads on Facebook at a time. So we essentially have a lot of tools to make that a lot easier, because otherwise it's really hard to do manually. So they've basically provided APIs, and we're one of the third parties that, provides tooling around it to actually make it, useful or manageable. Otherwise, it's impossible.
So Michael actually asked a question there that is a good follow-up there. Can you comment on the other views, i.e. by tag, etc., when sending a message in your example? How many writes in general will occur when sending a single message?
It's really going to depend on how many people are on the team. But however, they're all rolled up into one batch query. So there may be multiple writes in Cassandra, but it's all one query to Cassandra.
Yeah, effectively what we do is because it's in as a batch query, it gets put in as one write in the commit log, and updating your in-memory data is pretty cheap. So basically, we're not dealing with if there's 10,000 people on the team, we wouldn't be firing off 10,000 queries. We'd be firing off a handful of queries and doing a ton of writes all at once. And because those writes are all pushed together and they're all sequential writes, it's really fast. So Cassandra's strength is its write speed. So for us, we're really not afraid of distributing messages to 10, 100, or 500 people. It's all the same to us.
Okay, great. A different Michael asks, you said that many queries have to go against all Mongo nodes and that you have to manually shard, but doesn't Mongo handle sharding automatically and use shard keys to only target specific nodes?
It does. What we were talking about was in instances where your usage is kind of exceeding Mongo's ability to handle a single collection. If you have massive collections, is this not what we're talking about?
No, sorry. I think I heard the question a little bit differently. So basically, when you do a query against Mongo, if you're not using the shard key or the ID, Mongo does not know which shard the answer is actually going to come from. So it will actually have to contact all the shards and then piece together the sections of the query.
Okay, thank you.
Yeah, that's kind of where we were talking about the query flexibility. So you can do all sorts of wild stuff against Mongo, but ultimately you have to not do that if you have an application of any sort of significant size, because once you start hitting every node on every query, your whole database just drags to a halt. It's extremely inefficient.
Okay, and Jorge is asking, could you comment on, and by the way, this could get a lengthy response, so let's keep it short. Could you comment on the experiences of deploying and maintaining a Cassandra-based application?
Yeah. As far as deploying it, it's just an issue of bringing up more servers and having them join the ring. Typically, you'll want to do a little math on the tokens to see where you want it to come up. But that in and of itself hasn't been a big hurdle. I actually just migrated from one Cassandra cluster to another last night. It was it took a little time, but it wasn't anything too stressful.
Yeah, I think one of the things, we didn't really touch on this in this presentation, but we did on our last one, and in our 5-minute interview, that for us, Cassandra operationally is amazing. The amount of work that's been put into it in order to make sure that node outages aren't a problem and multi-DC stuff works. It is phenomenal from a reliability standpoint for us. It has been absolutely fantastic. So when we're messing around with things, we take nodes down all the time. It is such a resilient database. So maintaining it from an operations standpoint, super straightforward.
Yeah, there is a lot less DevOps overhead that you need to maintain a Cassandra cluster.
Yeah, and as far as developing against it, there's definitely a little bit of extra work that has to go into modeling your data up front, but I really don't think that's a bad thing. I think having a really good understanding of your data is something that you have to have. And I think more often than not, whenever you hear people talking about performance problems with their database, it's probably because they have no idea what they're really going to do with their data, and it's just a problem. So like I said, for us, it's great.
Okay, thank you. And but beforehand, you warned me not to ask you any questions about obscure NoSQL databases or NewSQL databases.
Okay, what is it?
Well, this one isn't obscure. I just wonder if you have any views on how Cassandra is different from HBase. And if not, I can take it at a high level, no problem.
Yeah, so we don't have a lot of HBase experience, really. So HBase, in my memory, still has a few more working components than Cassandra. I think it, I mean, truthfully, like, we haven't deployed it in production, so it's really hard for me to comment. I'm not an authority on it. I know that
I mean, architecturally, it falls into the master-slave category versus, Cassandra's peer-to-peer architecture, and therefore, Cassandra lends itself to, easy scale out and high availability that you can get working with HBase, no problem, but it brings in a level of complexity that Cassandra tends to avoid. So on the operational side, Cassandra tends to be more robust and easier to run. So certainly that's how we tend to hear about it from the community. So this one is specific to cqlengine roadmap. Is there a Breeze driver or API on your roadmap for cqlengine?
Breeze driver. I'm not sure I know what that is.
Yeah, I have no idea what that means.
So no, it's not on your roadmap. They pasted a link, actually, if you want to check it out. breezejs.com. breezejs.com. Another question related to cqlengine is what, if any, problems should I expect trying to integrate cqlengine into a twisted-based app?
None that I'm aware of. In fact, I do know of a company up in the Bay Area that is using cqlengine in a massive twisted code base. Yeah.
Did they hear any issues that you know of?
No. So far I've just heard good things from them.
Okay, great. So we didn't put out your contact info anywhere, did we? Or is that on? Yeah, here we go. So that was Robert asking that question. So, Robert, if you'd like to reach out to John and Blake, and maybe you guys can connect Robert with that user.
Yeah, hit us up. I should point out that my Twitter tag is wrong here. It's Blake Eggleston, but email is fine too.
Yes, Twitter. Twitter's the way to go. So Jonathan asked, is your cqlengine an ORM type product? If so, how do you map the relationships between entities? And how do you, by the way, this is the second Elasticsearch question, so I think this takes care of the other one. How do you use Elasticsearch? Do you use it to do queries related to your rolled up stats? And the other, by the way, just to kill two birds with one stone, the other Elasticsearch one was, how do you complement Cassandra with Elasticsearch? Do you duplicate a lot of data?
Okay, so I'll answer the cqlengine question first. Cassandra in general has no support for relationships, and neither does cqlengine. If you need to kind of roll your own into your cqlengine models, that's fine, but there is no support for any sort of inter-row relationships. Regarding Elasticsearch, we use Elasticsearch for any query that basically has a lot of parameters. So if you want to say something like, give me all users that are part of this team and are named Blake and, you know, whatever, that sort of query is going to be difficult to do with Cassandra because you're either going to, need to do a massive query and like do a bunch of client-side filtering, or you're going to need to like build a ton of tables for every single permutation. So we just throw that at the search index, and that those types of queries are handled very, very nicely by Elasticsearch. For most, all the like industrial strength queries that we do that like, you know, we're constantly doing as part of our day-to-day operations, those are in Cassandra. But for like the more obscure queries, we will use Elasticsearch. And yes, we do duplicate our data. Typically, we will throw it into Elasticsearch in a way that often doesn't look like the table, just because we put it in Elasticsearch to facilitate the way that we're going to be querying it, not necessarily being a correct representation of how it looks in Cassandra.
Yeah, and for example, in a lot of cases, the document that we put in Elasticsearch is an aggregation of several different tables.
Yeah.
So we might put in the user information. So in addition to the user information, we might put all the teams that they're on. And basically, a lot of metadata about the user that allows us to efficiently query for, you know, anything we want. Like the number, honestly, the number of permutations that we can do with our Elasticsearch index is uncountable. It's insane. So it's really convenient.
Okay, cool. I've got a couple of wide row questions coming up here. Ramakrishna asks, the case for wide rows makes sense when the data is already compacted to an SS table, as the data is stored as one row and readers picking the data from just one place. But how will it play out when the data is in multiple SS tables?
It'll have to do a seek for each one, but for situations where that's a concern, we use leveled compaction, which will only split the data between two SS tables at most. You want to do that?
Yeah. So the other thing that's important to keep in mind is that when you're looking for a particular key and column, there are Bloom filters, which basically make it so that you don't have to look at a particular SS table on disk. You actually know beforehand whether or not your data is there. So there's a lot of tricks that are used to make sure that you don't do unnecessary disk seeks. Okay,
great. And then the other wide row question is, how wide are your rows typically? Is it typically lots of narrow rows or fewer rows with lots of columns?
It really depends on what we're storing. I mean, some of the, like, obviously some of the message stream stuff has a ton of, it's a very wide row. The ad stats, again, another wide row. And then there are other stuff, you know, there are other objects that we store as just, you know, a single row. Like, for instance, messages are stored as a single row in Cassandra with just the message data and the message ID and some other metadata.
Yeah, I think our wider ones are probably a few 100,000 or a million right now. But I mean, Cassandra technically has support to go up to 1 billion. I don't know if anyone is really doing it or if it's practical to go that high, but I do know that some people are above 10 million, and it's not a performance problem. So I think the recommendation that we got was to try and stay under 100 megs per row.
Okay, and we've probably got time for 2 or 3 more here. Athananthi asks, what compaction strategy did you use for your use case? Is it leveled or size tiered? And for a write-heavy use case, which would you recommend? leveled or size tiered?
So we pretty much use, well, it depends. So our two clusters have different disks. So in our cluster with solid-state drives, we opt to use leveled compaction everywhere, and the reason for that is the trade-off is with leveled, it's a little bit more I/O to do the compaction, but you end up with your data in fewer SS tables. So we're actually going to be moving everything over to the solid-state drives because they're just so insanely fast, even on a even when you're seeking to random data, you've got sub-millisecond lookup times. On a write-heavy workload, I think the recommendation is size-tiered.
Okay, and this is a Mongo-specific one related to compaction. Can you compare, Stan asks this, can you compare the compaction strategies in Mongo versus Cassandra?
That's a tough one. I'm not intimately hold on a minute. I'm not aware of Mongo's exact compaction strategies, so that's a tough one.
Okay, no problem. If we can't answer a question, no worries at all.
My understanding of the compaction in Mongo is that it was something that had to be done manually versus something that's in Cassandra, which is part of the in process.
Don't you have to shut the node down in Mongo?
No, it runs when the it runs when the node is up, but I don't think it's something that happens like a compaction in Cassandra under a heavy workload. You're always going to have compactions, so it's just part of the process. It's like it's something that's just part of the tool versus something that's an administrative thing, like that you would run manually or automate to run like once a day or something.
Okay, great. And I think last question this will be, can you talk a little bit about why Elasticsearch versus Solr? Are you backing Elasticsearch with Cassandra or something else?
We settled on that one a while ago. I know that when Elasticsearch, I believe, has better support for setting up clusters of machines.
Yeah.
And the query language is a little trickier, but it's a bit easier to programmatically generate. I think that was the clustering and also the existing experience people had with it on the team were the two main reasons we went with Elasticsearch.
Yeah, I mean, fundamentally, all the same. Fundamentally, you can do all the same things.
I believe Elasticsearch also is supports much faster writes, or it can handle a lot more writes simultaneously, if I remember correctly. So,
it's funny in the Cassandra community, we see lots of users on Solr and lots of users on Elasticsearch. There's good. There are people using both, obviously. So if you have questions, hit up the IRC or the mailing list, and you can ask questions there on Stack Overflow, and usually someone dives right in and answers those.
Yeah.
So guys, we're at the top of the hour. Thank you so much. For everyone, I would like to flag the upcoming webinar. We're going to take 3 weeks off here. Let you guys have your turkey and stuffing and all that good stuff. And we will be back on December 12th, Data Model on Fire. That will be the third in Patrick McFadden's data modeling series. So if you haven't watched the other two, the first two, you can go to planetcassandra.org and view the past webinars there. That will provide a good baseline of education for that last in the series. And then just a reminder, we have our free online Cassandra training courses available. That's Java development with Apache Cassandra, and that is at the link on your screens. So, guys, thank you very, very much. We really appreciate it, and you know, look forward to a third part of this in 2014. We'll have to get brainstorming on a good follow-up topic for you.
Sure, definitely.
Sounds good.